All right, you guys, I wanted to go ahead and just at least show the work that we did in class and the answers here for anyone that wasn't there today. So, and then we'll finish up the rest of the review. So here's 9.1a. We talked about how to find a formula for the nth term of the sequence, including alternating. This formula, numbers 4, we could write it two different ways. N plus 5 over n or n plus 6 over n plus 1, depending on if you start at 0 or 1. We had that discussion. Okay? Then we're determining if these converge or diverge. And so far, what we know is geometric series test, nth terms test, and alternating series test. We haven't gotten to that yet because we didn't learn that until 9.4, I think. So anyway, this was mostly geometric or nth term. There's some answers for 5, 6, and 7. If you guys remember the formula for the sum of any geometric is a1 over 1 minus r. You'll want to know that. Okay. All right. Couple more. We have these all diverge by nth term test or geometric series test on 1 and 3. Either case, they diverge. All right. 4 and 5 both converge, though, by geometric series, and I got those sums there. Okay. Now, 9.2 was a little more tricky. We talked about how if you have trying to make a power series for this, we can use a1 over 1 minus r. So a1 would be 2, r would be negative 3. We multiply that out. Write it using sigma notation. Sigma notation is pretty simple, guys. You just take this to the n power and write it n equals 0 to infinity. Intervals of convergence where the radius has to be, absolute value of the radius has to be less than 1. And then show 4 terms in a general term for a series expansion using f of x to the third. Okay? Okay, we did this section. It gave it to us this time in a summation, and we wrote it as a function. So the function, remember, is first term and 1 minus r, and we know r is negative 1/2 to the x. Got our interval of convergence there. Then I listed out 4 terms in the general term, and we got to taking the derivative of that, and just taking the derivative of this term here, and then 4 terms in a general term, and then integrate that. Okay? All right. We already did 9.3 quiz A. Third degree polynomial. You guys remember we start with f of x, and we do f prime, f double prime, f triple prime. We plug in x is 1 to each of those, and that gives me my coefficients. And then we go x minus 1 to the 0, x minus 1 to the 1, to the 2, to the 3, and over the factorials. Okay, and then we used that to approximate 0.8. Then we said, if we want to approximate 0.1, would it be more accurate to use a Taylor polynomial centered at 0? And you would think yes, because 0.1 is a lot closer to 0. The problem is for this particular Taylor polynomial, if we did try to do it at 0, the derivatives would be like the derivative right here, 1/3 x to negative 2/3, evaluated at 0 would be dividing by 0, and you can't do that. So the derivatives don't exist at 0. Okay? Okay, so now let's get into the parts that we did not go over yet. Starting with quiz 9.3b. Okay, you guys, so this is giving me the Maclaurin series of a function, right? And it wants me to find f of 0. Well, if you think about this, f of 0 will be negative 1 plus 1/2 times 0 squared plus 1/3 times 0 to the third plus 1/8 times 0 to the fourth. And do you notice that every single term right here, that's going to go to 0, that's going to go to 0, that's going to go to 0. So f of 0 just equals negative 1. Okay? Now, on the second one, let's go ahead and find the first derivative. All right. I'm going to find the first derivative right here. And here's what happens. The negative 1 goes away. This is going to be 2 times 1/2, which will be 1x. 3 times 1/3, which will be 1x squared. 4 times 1/8, which will be 1/2 x to the third. And then n times n minus 1 over n factorial times x to the n minus 1. Okay? So that's my derivative for that. Now, the derivative at 0, well, as I plug in all these terms, 0, 0, 0, they all become 0. So the derivative at 0 is just 0. All right? Now, let's think about the 10th derivative. Okay, now this part's going to be a little bit tricky. So let's think about this real quick. All right? For every derivative, okay, so the first derivative, I brought the n down. I subtracted 1. For the next derivative, I'm going to bring the n minus 1 down. That's going to go to the n minus 2. Okay? For the next derivative, I'm going to bring the n minus 2 down. That's going to go to the n minus 3. All right? And this is like going to keep on going, okay? This is to keep on going in this pattern. Now, all right, when I wrote this, I thought that was going to help me to write it as an n minus 1 squared, but it's actually not. I'm going to put that here, okay? And so I'm going to actually put that out in front. Because what's happening as I bring each of these terms down, you guys, what is it creating up here? So it's n minus 1, and then I have n minus 1, n minus 2. I bring down the n minus 3, and then it's x to the n minus 4 over n factorial. Is this not just kind of creating n factorial right there? I mean, almost. It's not going all the way down to 0 yet, but you know, it's getting there, right? Okay, so my first, okay, so let's see here. See if we can follow this pattern. This is my first derivative, my second derivative, my third derivative, my fourth derivative. Can you guys follow this pattern? So I feel like my 10th derivative would have an n minus 1 out front. And there'll be n minus 1, n minus 2, n minus 3, all the way to n minus 9, right? X to the n minus 10. Okay, this is what my 10th derivative would be. Because like my fourth derivative was n minus 4. My third derivative was n minus 3. All right? And then it's all over n factorial. Okay, so this is going to be my 10th derivative at 0 is going to be all those going up to that point, right? Okay, so let's see here. So I was trying to think about how to explain this. Okay, all of the terms with an x in it are going to go to 0, right? All the terms with an x in it are going to go to 0. So it's only kind of like this first term that will be left there. Well, if all those go 10, 9, 8, 5, 4, 10, n minus 9, okay? And then that goes to 0, but it's the 10th derivative. What's 10 minus 1 is 9. So that's actually what f of the 10th of 0 is, just 9. Okay? Yeah, let's go with that. All right. Crazy. Okay, let's find f prime of x showing 4 terms and showing the general term. All right, cool. So the derivative of this, we kind of already did it right here, but we'll write it over again down here. The derivative of this is x squared, 1/2 x to the third. I got to do 4 terms. So the next one would be 2, 3, 8, 1/2 8. Oh, okay, let's see here. All right, so it's the n minus 1 term. This started at n equals, let's see, that's n equals 1, n equals 2, because that's 2 factorial, n equals 3, n equals 4, n equals 5. So it would be x to the 5, it would be 5 minus 1 over 5 factorial. And when I bring this down to make that my derivative, so it's 5 times 4 x to the 4th over 5 factorial. Well, here's the thing about 5 factorial. It's 5, 4, 3, 2, 1, so that will cross off. So my next term right here is actually just x to the 4th over 3, 2, 1. Okay, and we know 3 times 2 times 1 is 6. So I can just erase that and put x to the 4th over 6. So it's like kind of hard to see the pattern, but anyway, that's where that's going to go. All right, and then again, my derivative right here for my general term, it's going to be, let's see here. If I bring down the n, and then it's x to the n minus 1 over n factorial. Okay? Now, let me show you another way to write this, just in case you're on like a multiple choice or something like that test, right? You guys look, n factorial is n minus 1, n minus 2, n minus 3, n minus 4, dot, dot, dot. And what happens is the n's and the n minus 1's cancel out. So really, for my general term, I could actually put x to the n minus 1 over n minus 2 factorial. So that's like kind of an easier way to write it because the n and the n minus 1 got canceled out. All right? And then we just put plus dot, dot, dot. Okay? Okay, an equation of the tangent line to the graph of f at x equals 0. Well, let's just think about this real quick, guys. Y minus y1 equals mx minus x1. Guess what? Right here, this is x1 because it's x is 0. This is y1. This is m. So, because it's the derivative at 0, so it's x minus 0, y minus 1, or y minus negative 1, actually, sorry. And then m was 0. That's my equation of tangent line. Okay? All right, great. Let's practice. This is one of each type of test. You really want to know these. Okay? All right, so let's go ahead and say, oops. Okay, for this first one here, I'm going to list a few terms, right? So I have, if I start at 1, I get negative 2/3. If I go to 2, I get positive 4/9. If I go to 3, I get negative 8/27. If I go to 4, I get positive 16/81. Okay? All right, and then you ask yourself, is this geometric or not? Geometric is usually the easiest one to work with, like I think so. Geometric is pretty easy. When I look at this, it's multiplying by negative 2/3 every time. And then this next one is multiplying by negative 2/3. So this is geometric. Okay? A1 is negative 2/3 because that's what it starts at. And R is also negative 2/3. So we know that the absolute value is less than 1. Okay? And that's true. So this converges by the geometric series test. So that's one part of our answer. The next part of our answer is, well, what does it converge to? Well, remember my formula, A1 over 1 minus R. So it's negative 2/3 over 1 minus negative 2/3. Okay, so it's negative 2/3 over, if I add that, 3/3 plus 2/3 is 5/3. The 3's cancel out, so it's negative 2 over 5. Okay, so that's what the sum is going to go to for number 1. All right, let's look at this next one, you guys. As soon as you see something like this where we're very clear on what the limit as it goes to infinity is, I would go straight to that test, okay? So look, this says the limit as n goes to infinity of this, okay? And we know that because the degree of the top and bottom are the same, we know that that goes to 2/3, which is not 0. And remember, this is by the nth term test. This diverges. And that's all that you have to say. All right, as soon as you can show that the limit to infinity is not 0, it diverges. Now, this is not an nth term question because it's not, well, because it is going to 0. My terms are getting like smaller and smaller every time, okay? And it's not a geometric, but notice it's alternating, right? So here's how we do the alternating series test. There are 3 things. 1, it has to be alternating. Is it? Boom, boom, boom. Yes. 2, it has to be every term has to be getting smaller. Okay. Well, yeah, certainly every term is getting smaller. Pi over 4 is less than 1, right? So pi over 4 is squared to the 4th to the 6th. Those are getting smaller, and dividing by factorials are definitely getting smaller. So it has to be decreasing. And then I have to do the limit as n approaches infinity. Okay? And if it's alternating, okay, so this is the alternating for, let's see how I want to write it. Okay, so basically we're going to go, it's pi over 4 to the 2n over 2n factorial. Anyway, I know that that does go ahead and go to 0. But hopefully you guys are recognizing this as an alternating series test, okay? And you want to recognize this as a specific equation when we're looking at the evens. Do you guys remember what it is? Evens is cosine. So this actually sums to cosine x. And then if we look and see what x is just what we plug in right here. So this is the cosine of pi over 4, which is root 2 over 2. So that's what that one sums up to. And it converges by the alternating series test. So it alternates, it's getting smaller, the limit's going to infinity. Okay, and then the cosine of pi over 4 is just root 2 over 2. All right, killer. Let's look at one more. Whoo, guys, this was our remainder section. This is a little tricky for sure. And I need to have a calculator with me. Okay, alternating series, here we go. Approximate f of 0.5 using a 3rd degree Maclaurin polynomial. Okay, so f of 0.5. Now, 3rd degree means it goes out to x to the 3rd. So it's 1 minus pi, and then that's 0.5, plus pi squared over 2 factorial times 0.5 squared. It's alternating, so it's minus pi to the 3rd over 3 factorial 0.5 to the 3rd. And then I just type this in my calculator, okay? So I can just type this up. Now, you can, if it's only 4 terms, like it might actually be easier, you guys, to just type it in like that. I'll show you a summation in case you want to do it a little bit faster, but like when it's only 4 terms, I don't know. Okay. Okay, let me get my calculator to open up here. No, get smaller. All right. Okay. So I can just go ahead and type in 1 minus pi times 0.5 plus pi over 2 factorial. Oh shoot, I hit absolute value, dang it. 2 factorial. And then 0.5 squared. And then, I hope I'm typing this in right, pi over 3 factorial. Oh, that was supposed to be minus because I'm alternating. Times 0.5 to the third. I don't think that's right. What did I type in wrong? Minus pi over 3 factorial 0.5 to the third. Let me pause this to find my mistake. That did not take me long to find my mistake. Okay, you guys probably already found it. Silly Mitchell. It's pi to the, whoops, can't do it there. Pi to the second. Oh gosh. Okay, so let's insert pi to the second over 2 factorial. And then it's minus pi, insert, to the third over 3 factorial. Hey-oh, there we go. Whew, my bad, guys. Gotta write that out a little bit. Make sure I'm doing everything that I need to do in there. 0, 1, 6, 9, 4. Okay? Find an upper limit for this alternating series remainder. Well, remember with this upper limit thing, we just do next term. Okay? Now, the next term after this would be pi to the fourth over 4 factorial, 0.5 to the 4. Okay? So let's go. And this is probably why I should use alpha fraction anyways. So pi to the fourth over 4 factorial, and then 0.5 to the fourth. All right, and this gives me 0.2536695. Okay, so that's the upper limit for any remainder that I'll have, because remember we talked about how from here we're going to add and then subtract, and then add, subtract, add, subtract, add, subtract. But it's getting like smaller and smaller every time. So that's the upper limit of any remainder I might have. Okay? Oh, shoot. I should have switched back to here. I forgot you can't see what I'm drawing. Okay. So, yeah. Sorry about that. So my next term was this. And then again, it goes like up a little, down a little, up, down, until it converges. Okay? Okay, use your answer to find an upper limit for the value of 0.5. Well, all I'm going to do is that's the upper limit of the remainder. The upper limit of the value, you guys, is just adding these together, right? So my upper limit for my value at 0.5 is, I'm going to add these 0.01694 plus 0.2536095, and when I add those together, I get did I type in a number wrong? I did. That's a 6695. Dang it. Whew. Okay, so I got 0.27. I don't think I used enough decimals. All right, I was trying to do this fast, but guys, there is no doing this fast. Okay. All right, so let me go back to my TI equation over here. All right. And it's just easier to do it this way. I'm just going to go that plus that. Okay? All right. So I get 0.27. 0.6096337. All right. So that's my upper limit for my value of 0.5. Okay. Oh, okay, cool. All right. So I know that f of 0.5 is somewhere less than or equal to that. All right. Okay, so I know f of 0.5 is somewhere less than or equal to that. All right, express f as a simple function using an elementary series and find the actual value. Ooh, okay. Guys, it looks like we are doing n factorial every term, not every other term. So it definitely has something to do with e, right? Okay, so let's remember how this goes. E goes like this. It's all the derivatives of e, which is keeping 1, 1, 1. And then it's like x to the 0 over 0 factorial, x to the 1 over 1 factorial, x to the 2 over 2 factorial, x to the 3 over 3 factorial. This is what we're memorizing for e, okay? Plus dot, dot, dot. Now, what's the difference with this one? Well, all it's doing is it's plugging in something for all these x's, right? And it's plugging in this extra pi n for this x right here, okay? So what's actually happening, all right, is I have pi x to the n, okay? But otherwise, it's the exact same thing. I have pi x to the n. Also, it's alternating. How do I make it alternate back and forth? Well, I just make this thing that I'm like multiplying by negative. So it's actually e to the negative pi n. Okay, it's e to the negative pi. Well, actually, sorry, not n, x. I can't switch up my variables like that. All right? Because what's happening is it's like 1 negative pi x to the 0 over 0 factorial. That's my first step, okay? And then that one's 1 negative pi x to the 1 over 1. That was my next step. And then it's negative pi x squared over 2 factorial. That was my next step, and it became positive because I'm plugging in a negative, right? So this basically is going to go to e to the negative pi x. I just put a pi in there. And so use that to find the actual value of f of 0.5. So the actual value will be e to the negative pi times 0.5. Okay? So if I were to plug that in my calculator and go e to the, come down here, e to the, and then in parentheses, it's like pi times 0.5. Negative pi times 0.5. Get that negative in there. Okay, and I get 0.2078795, blah, blah, blah. Okay, and that is within this upper limit that I got anyways. It's like, doesn't go any bigger than that, certainly. Okay, all right. Whew. Last question. Lagrange error bound when a fourth degree polynomial centered at 2 is used to approximate g of 4. Dang. All right. And we're still using the same function, I'm assuming. Oh, no, we're not using that same function. We're using this function right here. Remove that. Okay. Lagrange error bound. What you guys want to remember about the Lagrange one is it's, well, I'll use g, I guess. It's g to the n. It's the nth derivative of the max. And then it's x minus the center to the n over n factorial. Okay? So the only thing that's different is we're using the maximum. M is the maximum on this value, x to c. All right? Okay, so check it out. So it's g to the 5, and then whatever makes that the maximum, right? And then it's, so that's just an m right there. Okay, and then it's just x minus 4 to the n, 4 factorial. This is my error bound, all right? Now, you guys, what this is saying is that the absolute value is less than or equal to 3. So what is the maximum that this derivative can be? M is the point where the maximum occurs. The actual maximum right here is 3. It says it can never go above 3. So it's basically 3x minus 4 to the n over, oh wait, hold on. Getting my stuff mixed up. I'm approximating g of 4. Sorry, here, hold on. Yeah, I'm approximating g of 4 but I'm centered at 2. So x is actually 2. Center is actually 2. X is actually 4, because that's what I'm looking for. And a 4th degree polynomial, I need to go 1 past it to find the error, so I need to go to the 5th degree polynomial to get that error bound. Gosh dang. Okay, let me rewrite this again. So it's g to the n, so it's 5 derivatives of the max, and then it's x minus c, and c is 2, to the 5, okay, over 5 factorial. But the whole key is that I know what this max is, and it says it's never greater than or equal to 3. So 3, and then it's 4 minus 2 to the 5 over 5 factorial. All right, and you can leave it like that, or you can go 3. 4 minus 2 is 2 to the 5th over 5 factorial, and you can like figure out what that is if you needed to. I can figure this out actually. So that's 3, that's 32. This is 5, 4, 3, 2, 1. Okay, and I can cross out like this. 2 goes into 32 16 times. 4 goes into 16 4 times. 3 goes into 3 1 time. And so it's just 4 over 5. And so that's my error bound. Whoo, guys, I know that stuff's a little tricky, but let's just do the best we can. I'll give you some formulas and stuff for tomorrow, and we'll just see how it goes. All right?